Hi, I'm David Rhyne, Artistic Director of SC Bach, and I'm pleased to introduce SC Bach's first virtual talk, Temperament in Bach's Keyboard Music. It's often stated that music theory is all about math. This is certainly true when it comes to tuning systems available and developing during the 18th and early 19th centuries. Who better to give such a talk than our own resident mathematician, Lee Hagglund? Dr. Hagglund is a member of the SC Bach Board, a bass in the Bach Choir, and a retired math professor at Wofford College. A native Minnesotan, Lee has degrees in math and German from institutions in both the U.S. and in Germany. Before retiring, Lee taught math for 35 years at Wofford. In this talk, Lee will provide some background on how music is created, especially dealing with intervals and scales. He discusses the various types of scales used today and tuning systems used in Bach's day. Finally, he proposes a possible solution to the question of how Bach tuned his keyboard instruments. SC Bach is happy to offer this first offering in our new programs for our fans. We hope you enjoy Lee's presentation and discover something new about Bach's music.
Hello, I'm Lee Hagglund, and I want to thank Dr. Rhyne, our Artistic Director, for his introduction. In this talk on musical temperament, I'll be presenting slides using Mathematica, software that gives me access to many high-level mathematical functions. Let me share that now. In the interest of time, I may spend too little on a particular slide. If you need more time to digest its content, simply pause the video. During my last semester at Wofford College, the administration gave me release time to deliver a last lecture to the college community. I decided to do it on the mathematics of musical temperament. My research for the talk culminated in a marvelous discovery that convinced me that we now know what J.S. Bach meant when he described a keyboard instrument as wohltemperiert, that is, well-tempered. We can define music to be any sound pleasing to the ear, the voice of a loved one or the bark of a beloved dog, but as a technical physics matter, we'll confine ourselves to music produced by vibrations in the air at varying frequencies. I'm going to just give you a little bit of background about how music is produced, some music theory that you never needed to know, which is why you didn't ask. Tuning and temperament defined, they're different, and making sense of musical intervals. By that I mean the unit cent is used in order to compare musical intervals. It's a logarithmic thing which we'll explain as we go. Then equal temperament and the mathematics needed to achieve it, and finally we'll get to Bach's wonderful solution. First, some background. Since my undergraduate days, I've found it useful to use lifetimes to help me comprehend ancient times. By assuming the biblical prescription of a lifetime as 70 years, 70. As far as we know, the systematic treatment of Western music began in ancient Greece with the Pythagoreans, roughly 500 to 350 BC. Taking the Pythagorean era at roughly 400 BC, that occurred 2,420 years ago, divided by 70, or approximately 35 lifetimes ago. The fact that only 35 people have been born and lived their lives of 70 years since the Pythagoreans makes them seem more immediate and real to me. Applying the same measure to Bach's time, he died in 1750, or 270 years ago, which is less than 4 lifetimes. I can't resist Sorry, little glitch there in getting to the right slide. I can't resist talking a little bit about the mathematics that is unavoidably intertwined with musical temperament. The Pythagorean Brotherhood was a quasi-religious order whose members considered number to be the essence of things. Integers, that is, whole numbers, played a leading role. The Pythagoreans also recognized what they called commensurable numbers, what we today call rational numbers, fractions of integers. Modern mathematics has established there are an infinite number of irrational numbers, and while it would take me at least one more talk to explain this in detail, the infinity of the irrational numbers is larger than the infinity of the rationals. Because of this, I've always taught my students the metaphor of the real numbers as a heaving ocean of irrational numbers, with little lifeboats called rationals floating around on the surface. These lifeboats have an amazing property. No matter how short your arms are, if you are drowning in the ocean of irrationals, there is a lifeboat within reach. In mathematical language, any irrational number can be approximated as closely as you want by a rational one. Historians disagree on whether the Pythagoreans eventually perceived irrational numbers. Today we know that properly tempering pitches on a keyboard instrument like a piano or harpsichord requires irrational numbers. After listening to this talk, perhaps the listener will join me in speculating that the Pythagoreans' inability to produce a pure musical scale using only rational numbers could have led them to the existence of the irrationals. Here's some music theory you never needed to know, which is why you didn't ask. Assuming you are familiar with the modern naming of notes, I will use the octave from middle C to the octave C above for demonstrations. The unit hertz is defined as 1 cycle per second. The modern standard has the A above middle C vibrating at 440 hertz and middle C at 261.63 hertz. However, it is now widely accepted that in Bach's time, the frequency of A in most musical settings was 415 hertz. I will use that standard in what follows. Assuming the temperament we will attribute to Bach in this talk, middle C works out to be 247.598 hertz. Here are some pitches so that you can hear and hear what they sound like. That's the modern A. Here's the A in Bach's time. Here's the modern middle C. And here's the middle C in Bach's time. The Pythagoreans discovered that a string made of a proper material vibrated and emitted a pleasing sound when plucked. Furthermore, other things being equal, the pitch of the tone increased as the length of the string decreased. They discovered that strings whose lengths had certain whole number ratios to each other sounded good when played together. Thus, in addition to melody, music was produced in harmony by playing these intervals together. When a string of length L1 is plucked at the same time as a string of length L2, they would sound an octave if the ratio L1 to L2 was 2 to 1, and a fifth if the ratio was 3 to 2, and so on. It was discovered later that the frequency of a vibrating string determined the pitch, and the ratio of the frequencies was the inverse of the length ratio. Since the frequencies are in direct proportion to the pitches of the notes, i.e. higher frequencies produce higher pitches, it's a bit easier to use the frequency ratios to discuss intervals between notes. That's what I'll do in this talk. In this slide, we see the inverse relationship between lengths and frequencies, and we can hear an octave and a pure fifth sounded. Here's the octave, and here's the fifth. The octave sounds like one note. The higher tone seems to have the same pitch while reinforcing the lower one. The fifth is clearly perceived as two tones, but with a very pleasing sound. It's no wonder the Pythagoreans were enchanted by that interval, and as we shall see, they carried that enchantment to its logical conclusion. Here are the rational number ratios that produce the best known pleasing intervals. We can also hear that not all rational ratio intervals are pleasing. There's the octave, the fifth, the fourth, what we now call a major third, and a minor third, and here's a 7 to 6 ratio, not so pleasing, and a 12 to 11, almost painful. To this day, mathematicians call the sequence 1, 1/2, 1/3, 1/4, etc. the harmonic sequence. In order to compose melodies, the Pythagoreans needed notes arrayed in a scale. Since the fifth was such a pleasing sound, they resolved to construct the scale using ascending perfect fifths pitched down into the same octave. By doing so, they produced a 12-tone scale which we still use today. In Western music, it's why there are 12 semitones in the modern octave, now called a chromatic scale. They assumed the 12th and final perfect fifth would pitch down into a perfect octave with the beginning tone, for which we will use C. And you see that here. Alas, it was not to be. That 12th perfect fifth overshot the octave C by an interval now known as the comma of Pythagoras. Let's look at the ratios needed to build the Pythagorean octave. These are the ratios that give the Pythagorean octave. Here's the Pythagorean C octave. The top one is off by that Pythagorean comma. Here's the chromatic scale according to Pythagoras. Here's the diatonic ratios. This is the do, re, mi scale that you're familiar with, the diatonic scale. Actually, these don't sound too bad, do they? Here's the true fifth. Now, all these sound pretty good, don't they? But the final fifth in this octave, F to C, is off by that Pythagorean comma. Musicians took to calling this the wolf fifth. It doesn't cause too much problem as long as the melody is played completely within the octave. But if one desires to proceed to melodies that employ multiple octaves, the wolf fifth really growls. That's one octave higher. And here's the wolf fifth 2 octaves higher. Now we're going to move on to tuning and temperament and define them. On this slide we see the definition of a tuning. Only rational ratios need apply. Now the Greeks, there were many Greeks who attempted tunings in order to get rid of that Pythagorean comma, but since they were stuck using nothing but rational ratios, they were never successful. And here's the definition of temperament. In the simplest terms, in order to play an instrument with fixed pitches like a piano or harpsichord so it sounds pleasing over multiple octaves, the fifths in the chromatic scale must be flatted by a total of 1 Pythagorean comma, or the ratio between each of the 12 semitones must be identical. As we shall see, Bach's temperament was an irregular one, but a particularly brilliant solution for playing in all possible key signatures. Now I'm going to give in to temptation and talk a little bit about the mathematics of equal temperament. This slide shows us what we mean by a mean proportional, which is something that we need for equal temperament, and it is related, in fact it is the same as what we call the geometric mean in mathematics. A number placed between two given numbers, a and b, so the ratios c over a and b over c are equal. Since c over a equals b over c means that c squared equals ab, we see that c is equal to the square root of ab. Proposition 13 of Book 6 of Euclid's Elements gives a straightforward, straight-edge and compass construction of the mean proportional. You lay off the two lengths a and b in one line segment. Then you find the center of that line segment and use the radius with your compass and draw a semicircle. Then take the point where a and b, the two a and b lines meet, and do a perpendicular until it hits the semicircle. Then what you have are two similar triangles, this little one and this bigger one, and the ratio of this side to this side is the same as this side to this side, and that gives you your mean proportional or geometric mean. Now when A is 2 and B is 1 is in the octave ratio, the mean proportional, of course, is the square root of 2. Here's a string of length 1 which shows where frequencies must fall to achieve a common ratio between each pair. The common ratios give us this string of equations, and I take all the ratios of the succeeding values, and since they're all equal, and since 2 over 811 is also equal to the same ratio, all of those equations hold. Now since that's the common ratio, let's call it x, and that means then that if you multiply x together 12 times, what happens is all the denominators cancel, and because of the 12 factors on the left, you get x to the 12th is 2, or x equals 2 to the 1/12th, that is the 12th root of 2. Here are the equal temperament pitch ratios. They're all multiples of the 12th root of 2. And one thing that's interesting is that you can use the Euclidean construction method to get all of these ratios if you know the cube root of 2. And if you take the cube root of 2 and anchor that right here, which turns out to be the ratio for the major third, then if you do the construction using these two numbers, you get this one. If you use these two numbers, you get this one. These two numbers, you get this one. And if you take this one and 2, you get this one, and then so on. And you can just continue that to its logical conclusion, and you wind up with all the proper ratios. One thing I was excited to learn about this was that the cube root of 2, of course, is the solution to the ancient Greek problem of doubling the cube. That is, starting with the cube of side 1 and using a straight edge and compass, construct a cube that has a volume 2 and not volume 1, and it requires the construction of the number, the cube root of 2, which modern mathematics has proved is impossible. You can't do it with just ruler and compass. And so the problem of mathematical temperament is mathematically equivalent to the Greek problem of doubling the cube. Now, Mersenne, a famous French mathematician who has lived in the 16th century, well, he straddled the 16th and 17th century. And of course, he's famous in mathematics for Mersenne primes, which are primes of the form 2 to the n power minus 1. But he came up with a particularly accurate approximation of the cube root of 2 and was able to use the geometric mean construction above to give a very good frequencies needed for equal temperament. So equal temperament improved greatly because of Mersenne. And notice that his approximation of the cube root, which is given here, 2 over 3 minus the square root of 2, is only about 2/1000ths off of the actual value. And there were the ratios that were needed for equal temperament, approximations to the exact values. Oh, how did that get in here? Well, if you already know about logarithms, this page won't be any mystery to you. But essentially what you need to know is that a logarithm is nothing more than an exponent. And the two equations, y equals a to the x and log to the base a of y equals x, are equivalent. Now, if you let u be a to the x and v be a to the y, you can easily see that the properties of exponents translate directly into the properties of logarithms. Now, we'll use base 2, since 2 is the ratio of the pure octave, and the 12th root of 2 is the ratio of the semitone. You don't have to understand everything on this slide, but these properties lead us to the use of the cent unit to measure musical intervals. Here's how cents are defined. They're a logarithmic measure of intervals. The octave is divided into 1200 cents so that each semitone measures 100 cents. If n is the number of cents in an interval with frequency ratio a over b, the formula in logarithmic form is log base 2 of the ratio is equal to n over 1200, and that converts to, in exponent form, to a over b equals 2 to the n over 1200. The use of cents in measuring intervals makes things a bit easier because we can add and subtract them instead of having to calculate a multiplicative ratio each time. Here are the equal temperament ratios and their cents. Now, a Pythagorean comma is 23.46 cents, and its ratio is 1.01364. That is the interval by which we have trouble with the Pythagorean scale. In this slide, I want you to hear some pitch differences so you can better understand what Bach would have heard while tuning his clavier or organ. I'm using pure sine wave frequencies for the illustrations, but vibrating strings or air columns have a richer timbre, and so the differences would be somewhat easier to hear on a piano or an organ. Here are two consecutive pitches just 2 cents apart. Remember now, a Pythagorean comma is 23 point something. This is 4 cents apart, 6 cents apart. A sensitive musical ear will start hearing that that second one is slightly higher. Here's 8 cents. I think most people can hear that that second one is slightly higher. And here we added a full Pythagorean comma. And there it's quite clear that that last one is sharp. Now I'm playing them simultaneously. Here's 2 notes separated by a Pythagorean comma. Hear that beat? Here's separated by 1/8 of a Pythagorean comma. The beat's much slower, but it's still there. 1/4 of a Pythagorean comma. 1/6 of a Pythagorean comma. One 1/12 of a Pythagorean comma. So you can hear what the problem is with equal temperament, which also has some difficulties. Here's the pure fifth. Here's an equal tempered fifth. The equal tempered fifth is flat by 1/12 of a Pythagorean comma. And you can hear that beat when you play them together. Here's a pure third. Lovely sound. And here's an equal tempered third. Sounds pretty darn good. But that top note is pretty sharp. It's sharp by almost 1/2 of a Pythagorean comma. And that's in the modern equal temperament. Finally, the good stuff. For a long time, music historians simply assumed that Bach could play across all octaves of the keyboard because he used equal temperament. He was well known to be very fussy about tuning his own instruments, and we have evidence that he could sit down and tune a harpsichord in about 15 minutes. But in 1722, Bach applied for a teaching and supervisory position in Leipzig. To impress those who would choose the winning candidate, Bach chose his famous sequence of 48 compositions called Das Wohltemperierte Klavier, not Gleichtemperierte, which would have said equal temperament. Wohltemperierte means well-tempered. These were two series of 24 preludes and fugues in each of the 12 possible key signatures, both major and minor. He sent a written copy of these compositions to the committee with this title page. Wow. I want you to contemplate this page for a moment. Why so ornate? The answer to that question mystified music historians until February 2005, when Dr. Bradley Lehman published his two-part article, Bach's Extraordinary Temperament, Our Rosetta Stone, in the journal Early Music. Dr. Lehman's contention? The loops at the top are nothing more or less than the key to how Bach tuned his clavier. Here we have a slide that shows where the pitches are, or what Bach intended, and he did his tuning from F to F, starting with F here, and of course it's clear that middle C should lie right here because of this C, and also it's attached to the C on the word clavier, and so then this 1/5 down is F. Now notice what's happening here. Inside we have two loops inside that bigger loop until we get to the C. Now Dr. Lehman talks about those loops, but as a mathematician I noticed something that he didn't mention, namely that those loops are counterclockwise. And to me that means what Bach intended was that you pull back twice in order to get to C, the fifth from F to C. So in other words, you should flat it by 2 units. And to go from C to G, another double loop, flat it by 2 units. G to D, another double loop, flat it by 2 units. D to A, another double loop, flat it by 2 units. A to E, another double loop, flat it by 2 units. And now there are 3 pure loops with no internal loops, going from E to B, B to F sharp, and F sharp to C sharp. Those were intended to be pure fifths. Now we go from C sharp to G sharp, and we have only a single internal loop. Again, counterclockwise, 1 unit flat. G sharp to D sharp, 1 unit flat. D sharp to A sharp, 1 unit flat. Now, look at the loops on the 2 ends. Dr. Lehman did not have a good explanation for this. As I thought about it, I assumed that Bach thought of this string as representing the circle of fifths, but to use it horizontally, he had to break it and lay it out with the loops representing his adjustments to the pitches. So it's the circle of fifths, but it's broken and laid horizontally with these broken ends. And then notice it's broken here, and then it was reattached here. And that little projection there seems to think that, or seems to indicate that it was attached, reattached. Okay, now, here's my speculation. Here's what Bach did from A sharp to F. As we go from A sharp to F and traverse the circle of fifths, here we go 1 unit flat because it's a counterclockwise loop. But then when they were joined together, over here we have, look at this, this is a clockwise loop. So that's taking it a unit sharp, and we're now even. And now 1 more clockwise loop, and now we've gone 1 unit sharp. And so in other words, from A sharp to F, the fifth is adjusted as 1 unit sharp. Now, what was the unit? We decided that these loops indicate units, and so if we look at that, we count a total of 13 units flat and 1 unit sharp, for a total of 12 units flat. Since overall the fifths, I don't know why I can't get this to show, the fifths must actually be adjusted by a full Pythagorean comma, and we have 12 units total flat. And so that means the unit must be a Pythagorean comma divided by 12. And here we have the circle of fifths as tempered by Bach. Notice that these are all two units, that is 2/12, 1/6 of a comma flat from here to here. And then here we have 3 pure fifths. Then we have 1/12 of a comma flat to here. Again, that's 1/12 of a Pythagorean comma. And then when we go from A sharp to F, as indicated by the loops, it should be 1/12 comma sharp. Now, Dr. Lehman did conclude that that 1/12 comma sharp does go from A sharp to F, but he did so simply on the basis understanding that the two Fs were in perfect octave. But the loops tell it all. Here's Bach compared to equal temperament. Now remember, equal temperament was 100, 200, 300, 400, and so on cents. And you can see that Bach's ratios are just a little bit off in each of them. The average deviation from equal temperament is only 3.5 cents. And as we saw, it took about 6 cents for people to start really hearing the difference in pitch. And so Bach's well temperament was very, very close to equal temperament. After I had done the research for my last lecture at Wofford, I called the Petrie School of Music at Converse College to find their piano tuner so I could see how it's done in modern times, expecting to see how equal temperament is achieved these days. The Petrie School is an all Steinway institution, so the man in charge of the pianos there tuned and repaired them. He was one of about 50 certified Steinway technicians in the U.S. His name was Benny Mixon, and he was enthusiastic about my coming over and sitting in on a tuning session. We sat down in one of the music practice rooms at a Steinway Baby Grand. He pulled out a tuning fork for the frequency of F below middle C and proceeded to temper the octave from F to F by listening to the fifths. Sound familiar? I was hearing the flatted beat patterns of those 1/6 commas and 1/12 commas central to Bach's tuning. Although he moved too quickly for me to be absolutely sure, I'm convinced he used Bach's temperament. Of course, after one octave is tempered, the rest of the keys can be tuned with octaves off of the tempered one. I asked Benny when he was done if that was Bach's temperament. He said he didn't know, but that he had learned it by ear from his mentor at Steinway. I found out he had already been diagnosed with cancer when I met him. I found that out later, and he died a couple of years later. I'm told he was adored by the music students at Converse. I hope he taught one of his successors at Steinway to tune by ear the way he did. Now, I concluded my lecture to the undergraduates at Wofford. There were more than undergraduates present, but I was really speaking to the undergraduates by giving them 5 suggestions for a happy life, and I thought I'd share them with you at the end of this talk. Make your living at something you love to do. I was certainly privileged to do that. I loved mathematics and I loved to teach it. Be easily entertained. A mathematician, all he needs is a blank sheet of paper and a pencil, and he's happy. Marry someone who's a better human being than you are. I hit that jackpot on that one too. Have a dog in your life. The humorist Will Rogers said it best. He said, if dogs don't go to heaven, then when I die, I want to go where they went. And finally, listen to the music of J.S. Bach, and your existence will be deeply improved. I'm showing you the bibliography. There are 2 pages here. And as you look at the bibliography, I especially recommend Lehman's paper, numbers 6 and 7. There are 2 parts to it, and he gives much more detail on analyzing Bach's temperament, much more so than I could include in this short talk. That's the first page of the Bibliography. And here's the second page. This is mostly the mathematical side of the thing, but of those of you who are interested, at least you'll have that available. Thank you very much for listening. I hope you enjoyed my talk.